let's discuss power factor. Power factor is unusual in that it has two names that mean exactly the same thing. Power factor is also called cos phi. We'll deal with this just in a little while, but they mean exactly the same thing. Before we continue with this, to help you with everything that we do, you must at this stage have completed handout 6, the key point recap, and video 10 that goes with it. You must have completed handout 7, which is about phasors and power factor, and video 11 that goes with it. If you haven't done that, you may get a little bit stuck. Okay, let's make a start. From a running cost point of view, the best state for an AC circuit to be in is with the supply voltage and current in phase. So there's a supply voltage, there's a supply voltage, there's a supply current, and they're in phase. That's the ideal situation. So there are 0 degrees between the current and the voltage. However, in the real world, many of our circuits, the majority in fact, end up containing a mixture of resistance and inductance, which gives us reactance. This results in us having a lagging power factor. What tends to happen is the current that comes through the supply looks like this. It's not in phase like this. The current lags the voltage. So here, in whatever this circuit is, it has a power factor. We will explain a little bit more about this later, but it has a lagging power factor simply because the current and voltage are not in phase. Let's take that a little bit further. I am deliberately going to repeat myself over and over. So here is a resistive circuit, and if we try and draw this out for a phasor diagram, there's the supply voltage and the current through the resistor is there. If we look at this circuit, the current that goes through the resistor, as I've drawn it there, is also the supply current. That's the current that comes out of the supply, so I could call it the supply current. Doesn't matter, both the same thing. If we move on to this diagram, which for example may represent something like a motor or a ballast in a fluorescent luminaire, or perhaps an electromagnet or some other device which has a coil, then we need to rethink what we're doing with the currents. Voltage is there, and the current through the resistor is going to be in phase. The current through the inductor is going to lag, like so, and the supply current is going to be the result of these two currents. So IR, IL, IS. Okay, so this bit we've met before. As mentioned just a few moments ago, in this particular circuit, because the supply voltage, which is there, and the supply current are not in phase, we have a power factor. We need to get this current in phase if we can. We have a phase angle, phi, and if we take the cosine of that angle phi, that's the angle between the supply voltage and the supply current, we can get power factor. Okay, so those words are basically just repeating what I've said. Cos phi is A over H. Hopefully you can realize from the work we've done earlier, this is a triangle. If I move this over here, I have a triangle IR, IL, IS, and we have the adjacent and the hypotenuse. And if I just put some numbers on, let's suppose this is 4 amps, This is 3 amps and this is 5 amps. In case you've missed it, I've just done a 3, 4, 5 triangle. The adjacent is 4. The hypotenuse, which is our supply current, is 5. That's going to give us a power factor of 0.8. Power factor will always be a number between 0 and 1, and there are no units. Let's just talk momentarily about the phase angle. If we have a power factor, we can go backwards and get the phase angle. Phi is cos to the minus 1 of the power factor. Put the numbers in your calculator and I'm hoping you'll come up with 36.9 degrees. Okay, let's just take a moment to talk about the cosines. Here we have voltage and current in phase. If they're in phase, literally drawn one on top of the other, then there is 0 degrees between them. So if you take the cosine of 0 and you put that in your calculator, you will get 1. If we look at this next diagram, the difference between the voltage and the current is 90 degrees. And if we do the cosine of 90 degrees with your calculator, you'll get 0. So back to this diagram, when the voltage and current are in phase, the power factor is 1. That is the situation we want. If the angle is any bigger, moving away from in phase, then we have a power factor, and that is potentially a problem for us. It's going to cost us more money to operate a piece of equipment. Let's take this just a little further. So that's explained roughly what a power factor is. Power factor costs us money. Energy is wasted because we have a coil of wire in the circuit. So we need to look at correcting it, and correcting it is very, very inexpensive. First thing, the aim of power factor correction is trying to get the supply voltage and current as close to in phase as possible. Before we proceed, you need to remember the bits that we've covered in the previous handouts and videos. An inductor and a capacitor behave as absolute opposites in an AC circuit. With that in mind, let's just go through these routines again. Parallel circuit. Let's do it down here. Here is the voltage. Oops. And we have IR. It's going to be in phase. We have IL. It's going to be 90 degrees down. And the resultant supply current is going to be there. IS with a phase angle phi. So this is the problem we have. We're running a motor, an electromagnet, a solenoid, whatever it is, and it's giving us a lagging power factor. If we just stop and look at this diagram for a moment, and I put some numbers on it, only the resistive current does useful work. 4 amps. So it's 4 amps that we need to run that motor. However, because of the reactance of the coil of wire, it creates a 90 degree shift, and the resultant current that comes through the supply is 5 amps. Quick look at this. This is 25% bigger than that. So just because we have a coil of wire, a motor, a magnet, a solenoid, whatever it is, in a circuit, it's going to cost us 25% more to run it just because it's got a magnet in it. So we need to find a way of getting around that. Let's take that to the final step. So this is the circuit we had on the previous page, the one we've just been looking at. Let's do the phasor diagram again. And the only difference is I've added in a capacitor. Here is our supply voltage. The current through the resistor, IR. Voltage and current are in phase in a resistor. Current through the inductor. Current lags voltage in an inductor. Oops. The current through the capacitor. Current leads voltage in a capacitor. And this is the magic of it. We would calculate the value of this capacitor to take the same amount of current as the inductor takes. And if we remember that at any instant in time, the current through the inductor and the current through the capacitor are total opposites, then what we've done by incorporating a capacitor into the circuit is we've created two identical and opposite currents, which basically cancel each other out. And we're back to a situation where the current that is going through our supply is now just the resistor current. Okay, all the currents are flowing, but the inductor current and the capacitor current cancel each other out. This is power factor correction, and adding a capacitor to an inductive component like a motor is the most popular way of correcting power factor. The cost of a capacitor may be something like £1, and adding a cost of a £1 capacitor to a motor that is going to cost hundreds of pounds in its life to run, this will save us hundreds of pounds over the useful operating life of the machine.